We have one more reaction, nucleophilic addition reaction, that uses carbon nucleophiles. Just to put in the notes, we've already looked at Grignard on the worksheet, and then we also looked at cyanide, forming cyanohydrins, on the worksheet as well. And so the last one that we're going to look at is called the Wittig reaction. That is pronounced Wittig, not Wittig, Wittig reaction. And here's the generic look at the Wittig reaction. We can do this reaction with either an aldehyde or ketone. I'm just going to draw it with a ketone. This reaction uses a crazy looking reagent. It's carbon. It's got a couple things attached to it. We've got variety of what could be attached out here. And then it has a double bond to a phosphorus. And that phosphorus has 3 phenols on it, which I'm abbreviating PH3. The product of this reaction is going to be an alkene, and that alkene, that carbon, is going to have on it whatever we started with. This little guy right here, this reagent, is called an ylid, pronounced ill-id. So this is an awesome reaction because it forms a carbon-carbon bond. Specifically, it forms a carbon-carbon double bond. But it's one of the few ways that we have of creating carbon-carbon bonds. So this reaction is really mysterious. It looks like it's just full of all kinds of magic. The first thing that we're going to learn about with the Wittig reaction is just the synthesis of the ylid. Like Grignards, ylids are made as you need them, and they are synthesized from an alkyl halide. This alkyl halide can have any halogen on it that we want. It has to have at least 1 hydrogen on it, but the other 2 groups on the carbon can be whatever we want them to be, and they should be whatever we're trying to put onto the alkene ultimately. That's the whole goal here. This is going to be an SN2 reaction. So we have the same type of rules as we would have for any SN2 reaction. Best case scenario is that we have just a methyl halide, a CH3X. Next best scenario would be a primary alkyl halide with 2 hydrogens on there. And we're okay if we have a secondary alkyl halide, but the reaction is going to slow down quite a bit. So in this, we're going to do a 2-step reaction. Step 1 is this PPH3 reagent. I'm going to draw a picture of that for you. And step 2 is butyl lithium, which is a really strong base. Let's draw the PPH3 over here. This is a phosphorus, and this phosphorus has 3 phenyl groups attached to it. So what this ends up making is the phosphorus with the 3 phenyl groups that is bonded to carbon atom, and it has retained those, whatever those 2 extra bonus things are on the carbon. It's lost its hydrogen and it's lost its halide. The carbon has a lone pair of electrons on it, which is where its nucleophilicity comes from, and the phosphorus has a positive formal charge. And this is the true structure of the ylide. There is a resonance structure that we can draw for the ylide that helps us understand, makes it make a little bit more sense and helps us understand the stability of the ylide. This is where we have a phosphorus-carbon double bond, and that's the form of the ylide that I drew up when I drew the first generic reaction. This particular, the form with the carbon-phosphorus double bond, this is not the major structure. Well, and if we think about that, it makes sense that this version would be the major structure of the ylide, because we do know that this is a very good nucleophile, so it's got to have a negative charge on it so that it can go attack our carbonyl carbon. However, a lot of times, and a lot of people, myself included, prefer to draw the carbon-phosphorus double bond structure of the ylide because it helps us visualize the Wittig reaction. So this is a good visual tool for predicting the products. So even though I know that the carbon-phosphorus double bond is not the main structure, I still like to draw it that way because it helps me predict the products of the reaction. So this is a reaction that we're not going to learn the mechanism for, which is nice because it is a pretty crazy mechanism. We're just going to go straight to predicting the products of a reaction. That is definitely not what I wanted to draw. This is a ketone that I wanted to draw, and we are going to react our ketone with this ylide and predict the products of this reaction. The way that I like to visualize it is breaking the carbonyl compound apart at the carbon-oxygen double bond, and also breaking the ylide apart at the carbon-phosphorus double bond, and then putting those pieces back together. So I'm going to retain everything but the oxygen from my carbonyl compound, and then I'm going to just tack onto that carbon the R group from the ylide. And that's it. That's all I make. We are making an alkene, so that means we need to look out for isomers. I'm just going to write E and Z. It could also be cis and trans. If you are making E's and Z's or cis and trans molecules and you're being asked to predict the major product, we're just going to be thinking about normal steric hindrance and normal stability of alkenes anytime we form alkenes. Let's also practice, before we finish this, let's practice predicting how we would get that ylide, where that ylide comes from, because that's going to be something that's important for us to know as well. So when we form the ylide, we know we always have to use PPH3. We know that we always have to use butyl lithium, BULI, that's part of the reagent. We also know, when we look at the ylide itself, that these components of the ylide came from the original alkyl halide. So those parts are definitely there. The alkyl halide, if we look back up at our reference here, the alkyl halide also has attached to it a hydrogen and a halogen of our choice. So that would be the appropriate alkyl halide for this reaction.